Limit Laws Part 3. Now it's finally time to look at what to do when a limit cannot be determined by substitution alone. We call these cases indeterminate. And when something is indeterminate, that means that we need to do more work. But what does it mean to be indeterminate? Well, let's look at these two functions. We have f of x is equal to 5x and g of x is equal to 2x. If we look at the limit as x approaches infinity for 5x, we can tell that as x is going towards infinity, 5x is also going towards infinity. And if we look at g of x is equal to 2x and the limit as x approaches infinity for 2x, as x approaches infinity, g of x, that 2x, is also approaching infinity. But these look a little different. They both approach infinity, but this 5x is much steeper than this 2x. So something interesting happens if we try to look at the limit as x approaches infinity for the quantity of 5x minus 2x. Well, if we try to use our limit laws to split this up, we end up with the limit as x approaches infinity for the 5x, which is infinity, minus the limit as x approaches infinity for 2x, which is also infinity. So we end up with this infinity minus infinity. Okay. And if we look at the limit as x approaches infinity for the quantity of 2x minus 5x, well, we can also split this up with limit laws. So we have the limit as x approaches infinity of 2x, which is infinity, minus the limit as x approaches infinity for 5x, which is also infinity. So we get another infinity minus infinity. But not all infinities are the same infinity. If we take a look at this 5x minus 2x and try to simplify that, because we can follow that order of operations as well, 5x minus 2x is equal to 3x. So we can look at this limit, and we have the limit as x approaches infinity of 3x. And the limit as x approaches infinity of 3x is equal to infinity. But if we look at this limit as x approaches infinity for the quantity of 2x minus 5x, well, 2x minus 5x is equal to negative 3x. So this is the same as the limit as x approaches infinity for negative 3x. And as x approaches infinity for negative 3x, we get that the limit is negative infinity. So when you have infinity minus infinity, we have to think about which infinity is bigger or moving faster. And for more complicated functions, we can't always tell exactly which one is moving faster. So we have to be able to do more work. Sometimes the do more work is as simple as combining like terms. Sometimes it gets a little more complex. So again, one of the reasons we cannot do algebra on infinity in our number system is that not all infinities are the same. Some functions are approaching infinity much more quickly than other functions. Also, limits tell us what a function is approaching, not what it actually reaches. So functions with holes and asymptotes can often be indeterminate if we just try direct substitution. So let's take a look at the limit as x approaches 1 of the quantity x squared plus 2 over the quantity x minus 1. If we try direct substitution, we're going to end up with 1 plus 2, because 1 squared is 1, over 1 minus 1, which gives us 3 over 0. And we just can't really tell what's going on there. So sometimes we have to look at a picture of a graph. If we look at this graph, we can see as we're approaching 1 from the right, the limit goes to positive infinity, and as we approach from the left, the limit goes to negative infinity. Since these are not equal, our overall limit does not exist. If we take a look at the limit as x approaches 1 of x squared minus 1 over x minus 1, we end up with 1 minus 1 over 1 minus 1, and I can write the squared if that makes that more clear, which gives us 0 over 0. But if we look at the graph, and we approach from the right, we see that we are approaching about 2. And if we approach from the left, we also see that we're approaching 2. So the limit as x approaches 1 for this function is 2. And then finally, if we take a look at the limit as x approaches 1 for 1 over the quantity x minus 1 squared, if we try out direct substitution, we end up with 1 over 1 minus 1 squared, which gives us that 1 over 0. And again, we don't know what this means for a limit. We're like, that's not quite right. You gotta do more work. So if we take a look at this graph, and we look at the right limit, we see that from the right, this limit is approaching infinity. And taking a look at our left limit, we're also approaching infinity. So the limit as x approaches 1 for this function is positive infinity. Here are the official indeterminate forms that whenever you see them, that should tell you that you need to do more work. So if you see a 0 over 0, a positive or negative infinity over a positive or negative infinity, an infinity minus infinity, an infinity to the 0 power, or a 0 to the infinite power, you need to do more work. The first 3 of these we'll be working with in this section. However, the last 2, these these exponential indeterminate forms, we'll be working on later in the course. It has to do with the fact that when you're approaching something, so taking a limit, it doesn't mean that you actually reach it. So one of the cases where we approach 0 but don't actually reach 0 is with asymptotes of exponential functions. And how these indeterminate forms work out is going to have to do with how quickly you're approaching 0 and whether or not you're approaching 0 from above 0 or approaching 0 from below 0. That's going to have a lot of impact on whether you have something negative or positive and whether you have a big number or a small number. So again, that's later in the course. We're going to mostly look at these guys for now. So when we see an indeterminate form, we know that we need to do more work, but that more work we need to do varies. We might have to factor or expand. We might have to multiply by the conjugate or the least common multiple. We might have to combine rational expressions, or sometimes you just have to graph the function. What you'll notice is all these strategies are going to combine a lot of your prerequisite skills. So if you're struggling with this section, it probably means you need to practice your algebra a little bit more. But keep in mind, when evaluating a limit, you should always try direct substitution first. You want to show that you have an indeterminate form, and that's why you're going through this long process of making it so that it can actually be determined. Let's take a look at an example. We have the limit as x approaches 3 of the quantity x squared minus 9 all over the quantity x minus 3. The first thing that you always want to try is direct substitution, so we will substitute 3 into our function. So we have 3 squared minus 9 all over 3 minus 3, and that was our direct substitution. Then we want to simplify this. So 3 squared is 9, and 9 minus 9 is 0, and 3 minus 3 is also 0. This is one of our indeterminate forms, which means that we must do more work. But what work do we do? Well, when I look at this, the main problem that I have is with that x minus 3 in the denominator. We're okay with a 0 in the numerator as long as the denominator is something other than 0. But a 0 in our denominator is always going to cause trouble. So I know that in some way I want to make it so that that x minus 3 is not getting in my way. The next thing I notice is when I look at this x squared minus 9, that is a difference of squares, which is something that is usually pretty easy to factor. So I'm going to try factoring it and see if something interesting happens. Notice that I am writing this limit as x approaches 3 because I have not yet evaluated that limit. Before you evaluate a limit, you can't stop writing it. That would be the same as having 5 plus 3, and then you decide, you know what, I don't feel like writing that plus 3 anymore. I'm just going to write the 5. It's not the same expression anymore. The limit is important. So we have the limit as x approaches 3 of, I'm going to factor my numerator, so x squared minus 9 factors to the quantity x plus 3 times the quantity of x minus 3. And then my denominator stays that x minus 3. So that was factoring. When I look at this, I get very excited and very happy because I see an x minus 3, that whole quantity x minus 3 is one of the factors in my numerator, and I see that one of the factors in my denominator is also that x minus 3. So that means I can divide out these common factors. In the numerator, I'm left with that x plus 3, and then in the denominator, I'm left with a 1. So this is equal to the limit as x approaches 3 of x plus 3 over 1. And the limit as x approaches 3 of x plus 3 over 1 is just the limit as x approaches 3 of x plus 3. And now I can use direct substitution. So I'm going to directly substitute my 3 in for x. So this is equal to 3 plus 3, which is 6. So the limit as x approaches 3 of x squared minus 9 all over the quantity x minus 3 is 6. And that is how you use factoring in order to evaluate a limit for an indeterminate form.